Welcome to the webinar on the subject Sensor-Centric Data-Intense Approaches to Manufacturing Operation from Cradle to Grave. Please let me introduce MDPI. MDPI is a pioneer in scholarly open access publishing. MDPI has supported academic communities since 1996. Based in Basel, Switzerland, MDPI has the mission to foster open scientific exchange in all forms across all disciplines. Our 429 diverse and open access journals, including 420 peer-reviewed journals and 9 conference journals, are supported by more than 150,000 academic experts who share our mission, values, and commitment to providing high-quality service for our authors. Sensors is the leading international peer-reviewed open access journal on the science and technology of sensors. Sensors provide an advanced forum to the science and technology of sensors and its applications. Here is the short timetable. Dr. Janice Turpany is our chair. Also today, Dr. Lihui Wang, Dr. Paulo Costa, and Dr. Vincent Paquet will have their presentation about 25 minutes. Also, after the presentation, we will have the Q&A section moderated by Dr. Thomas Kerfes and Dr. Kyle Salibi. The relevant special issue, which is related to the topic of this webinar, is sensors for machine condition monitoring, diagnostics, prognostics, and maintenance, with the deadline for the manuscript submissions on 25 January 2024. If you are interested to contribute, you can find the link in this presentation. After, you can post your questions in the Q&A box, but please do not forget to mention the name to whom the question is intended. Today, our chair is Dr. Janice Turpany from the Department of Systems Engineering and Operations Research and the Department of Mechanical Engineering, George Mason University. Today's presenter is Dr. Lihui Wang from Department of Production Engineering, KTH Royal Institute of Technology from Sweden. Dr. Paulo Costa from Department of Systems Engineering and Operations Research, George Mason University, USA. And Dr. Vincent Paquet from Electrical and Electronic System Research, Oak Ridge National Laboratory. So thank you once again. Dr. Janice, please, you can continue.
Okay, so welcome. Thank you so much for joining us today. It's really truly an honor to be part of this outstanding group of researchers and thought leaders to present to you today. I will have to apologize. Dr. Tom Kerfes is unable to join us today. Late breaking news, he's being sworn in on the Navy and Science Technology Board here in the United States. He'll be meeting at the Pentagon with the Secretary of Navy. So one of his close colleagues and also an outstanding researcher in all rights himself, Dr. Kyle Salibi will be helping us with the question and answer period. So as you saw on the website advertising this webinar, we're going to cover a variety of topics that are all related to sensor-centric data-intense approaches to manufacturing operations. The key here is that we're really looking at this from the viewpoint of from cradle, from inception, idea through grave. And that includes, of course, longevity during operation as well as retirement. And our experts today will touch upon topics that they have been quite involved with. And I believe that you'll find quite a lot of wonderful insights and experience in this webinar. As was pointed out by our colleagues at MDPI, there is, Dr. Kerfus and I are co-editing a special journal, and we strongly encourage you to consider submitting your scholarly works to that special issue with the deadline in January. So with that, let's go ahead and get started. And our first presenter is Dr. Wang, who will speak with us for about 25 minutes.
Thank you, Janice. So I will start with the first presentation focus on brain robotics, especially for human-centric collaborative assembly. Here is my presentation outline. I will focus first on the background information, and then talk about the concept of brain robotics. Then I will mention one specific application, research application, especially focused on stimulus-free brainwave-driven HRC, human-robot collaboration for assembly. There's another one is stimulus-based, which is relatively simple. I will not touch upon because of time. Finally, I draw some conclusions and identify the existing challenges, future research directions. The first question naturally people ask is why human-robot collaboration? We have used robots for many years, but robots especially is for automation purpose. Now we have a need to use a robot to assist and help a human being to do more complex work that still rely on humans' experience, skills, and expertise. When we put a human into a robotic cell, there's a number of challenges. Here is how robot can really learn from human operators. I'm talking about the experience of the operators. Fortunately, today we have a different AI learning algorithm. We can use the AI algorithm to identify the pattern if we put a camera around to capture the motion of the human being. The pattern will be identified, and this will be converted to the robot motion as one example. And robot can learn from experience of the operator day by day and getting smarter and smarter. However, normally we use pre-generated control code to control robot, as mentioned in many automation scenarios. But in this case, when we add a human operator to a robotic cell, it's in a dynamic environment. We cannot use a pre-generated robot control code, but have to use a different modality to control the robot. Example, we can talk with the robot, use a natural language. Hopefully, robot can understand the command. We can also use a hand gesture to send our command to the robot. Of course, this requires additional processing systems to convert the high-level command to the low-level control code. There's another way to use our brainwave to directly control the robot. No matter it's talking or use a gesture, whatever our motion is controlled by our brain. If we can use the brain directly to control the robot, we can bypass the unnecessary speaking and gesture. Those sometimes may not be reliable in a noisy environment or when the operator is busy with both hands occupied. So this sets the scene for the human-robot collaboration and especially to use brainwaves. Now let me introduce briefly about the concept of brain robotics, what it is. This really brings the most intricate, complex, and fascinating elements to robots. Our brain is quite complex. If you look at the diagram here, illustration, a human brain has 86 billion neurons. And these neurons send and receive information. The information passed by through the so-called synapses. Once the difference on both ends of the interface develop certain potential, signals will pass through like a spark. And this can be generated at high speed and high frequency, pass the information on. However, the strength of the signal is very weak. Neurons communicate through these electric signals. It can basically pass by all the informations we use, no matter what we see, feel, touch, and think. All those information can be passed by. Today, we can use electrode to capture our brain waves in order to process them and understand them better. So here you can see a very complex structure of the human brain, as well as their functionalities. I will only touch these 8 sensory inputs. The sight, we receive input from outside world, smell, and taste, touch, and hearing. These are the common senses, was the 5 most used senses we use today. But in addition to these 5, there's also balancing and acceleration to keep ourselves in a good condition. And for motion, we need to get joint positions as well. This is also considered as input. And eventually, these facial impressions are also important. In terms of brainwaves, it can be classified into different frequency range. The first one is called a delta wave. This is from 0.5 to 4 Hertz. When we are asleep, unconscious sleep without a dream, normally is in this range. The next level is the theta wave from 4 to 7 Hertz, still sleeping, but with dreams. Alpha wave is from 7 to 13 Hertz. This is especially when we are relaxation mode with eyes closed, but still awake. For the operators, we focus on this range, the beta wave and the gamma wave is from 13 to 100 Hertz. This is especially when human awake during the working mode, the brain activity is in this range. Human brain action is controlled by different parts of the brain. Mainly, it can be divided into 4 parts as listed here in this circled number and explained in this table. The first part is frontal. You can see the different functionality listed here. Parietal, interpreting languages, and occipital, mainly is for visual processing, and temporal for language understanding. This also stores long-term memory. When we try to use this silent thoughts to control the language, control the robot, we can use a language. This language can be silent language. We think in our brain, like move, to move the robot. Naturally, we use this part of the brain. We can use our memory. The operator may be an experienced one and in the past already operated a robot and use the past memory to control the robot. It's related to section 4. If use a vision, imagining that robot is moving, you use your vision capability, and this is related to this section 3. Control the same movement. Perhaps we can use a different part of our brain, and holding a single thought over time is also difficult. It's very subconsciously we switch from one way to another, and how to process this brainwave is a challenge. Nowadays, we control the brainwave, use the EEG signal, and then eventually control the robot. But what is the EEG? EEG stands for electroencephalography, and there's a number of different commercial devices can be used to collect EEG signals. Here, listed 6 of them, based on the signal to noise ratio and proportion to artifact. We can see the last one, G ladybird, is the best one to use. Of course, this one also more expensive compared with others. And this use the wet approach. The electrode needed to put some liquid or gel to increase the conductivity. For our research, we use this one, G Nautilus, and this one shows on the picture has 64 channels. We use a 16 channel for academic research. If we can properly retrieve, collect brainwave signals, the brainwave can be sent to the computer for processing. After identifies the patterns, we can then convert it to so-called function block and eventually to control the robot. Signal processing is the first task we need to carry out. EEG signal, as I mentioned earlier, is very weak in terms of strength or the amplitude. And easily it can be affected by the noisy environment at different steps along this chain. Different artifact or noise can be introduced to the original signal. So amplify them, signal acquisition, and so on. We also need to follow this signal processing chain. Eventually identify the pattern and control the robot. If the audience are interested, can check some of our previous publication for details. For the sake of a limited time, I will move on. So sensor placement and system configuration is listed on this slide. Sensor should follow certain patterns to place them. This is called a 10-20 pattern. You either from the forehead to the back divided into 10 or 20% and place the sensor in that area, or from the left to right. That's another way. Once we wear this sensor headset, we can also wear a safety helmet in the factory environment. So this is an illustration of our lab environment. We have a robot and workstation and human operators wearing a sensor headset. Of course, it's a networked environment. Data can be retrieved, sent to the computer for processing. And system architecture is also needed in order to process the information. In this case, sensor data are collected from the EEG sensor headset and goes to the command phrase phase, collect this command phrase, process them, and divide them into proper control words. And these control words eventually can be converted to function blocks, predefined function blocks. At this stage is a macro control command at a higher level, and a function block will generate internal control command and send it out to the robot controller. This is the microcontrol command native to the specific robot controller. Let me briefly mention how to process the brainwave and convert them to a control command. A simple way is to use a structured command, and this control command we call it a control phrase. It has 3 parts. The first part is the subject, the executor. Second part is the predicate, the action, and the third part is object, the component, what needed to be assembled, for example. And this in the time domain occupy different duration. Then we send this information and chop them off to the 3 parts, 3 shorter sections of brainwaves. They are in the wave form. We call it a control word, CW. And this section related to the subject, and this related predicate, and so on and so forth. Then we can use the continuous wavelet transform to convert waveform into images in the time frequency domain. So this horizontal axis is the time, this is the frequency. And then we can apply learning algorithm. We use a convolutional neural network because CNN is good at processing images, and we therefore convert the waveform to images. After processing, of course, the first part is training, and eventually we can use the neural network properly to identify the three part, and which is in, for example, the robot has screwdriver, and we can control the robot. There are different challenges, which one to use. This has been done and compared. Eventually, we use MOLET. This has a high risk level value of energy to entropy ratio. Visualization is another way to observe how our brain wave, focusing on this time frequency domain and the sensor placement, then we can see how these signals over time can be converted to the time frequency domain images, as shown in this slide. So that section of the images in wave is converted to images. As one example, we define a different subject, predicate, object, and they can be combined to a limited set of a control command. This can be resided in a database or library. Based on the assembly operation, we can define more and more control words and use them properly. And this is one type of CNN, convolutional neural network. What we use it is VGG16. Using VGG16, it is pre-trained already. We only need to add a few data. The data compared with the original training is much less. We use about 10,000 data for training, 4,000 for validation. Eventually, the VGG16 really works. This is a comparison. Our approach compared with other benchmark algorithm, obviously VGG16 performs much better in terms of training and testing. The other concept I mentioned earlier is macro-micro control command. When we try to control robot, if we use control microwaves, like controls the tiny movement of a robot, is impossible. We have to use a high-level command first, then convert them to the native control command of a robot. One possible way is to use a function block, as illustrated on this slide. This is a function block, receives input and generates output. On top is as the events, bottom as the data, and inside there's different algorithms that can be used. If we put function blocks properly, we can use this function block network to control a more complex robotic assembly environment. Inside of function block, it uses a finite state machine. Whenever a state arrives, triggers the internal algorithm and generate a result, and the result will be output for the next function block or send it to the robot controller. So the idea is from the brainwave patterns, it receives a high-level control command, passes through the function block network, and eventually control the assembly operation. In this case, one example is to pick up a key pin, follow a certain trajectory generated at runtime, and inserting them. There are some reference information. Where is the pin? Where is the feeder? Where is the workbench? All those are available. We consider it's a given or can be identified by camera or through other type of sensors. So here I wanted to show you one example. And this example involves one human operator, one robot, and some surrounding equipment, sensors, and so on. So here comes the conclusion part. As a recap, today I presented three topics, main topic. One is a brainwave-driven approach for human-robot collaborative assembly. There are two basic approaches. One is a stimulus-based. Stimulus I didn't present today. Mainly is you can use the sound or use the images, use the lighting to stimulate your brain. Whenever you see something, hear something, that's a reaction. Your brainwave will change, but that's more passive. What we consider is more challenging is a stimulus-free. Let operator to consider a command, either use a speech, use a memory, or use a vision to control the object or assembly operation. That's the first part. The second part, what I presented is one additional modality. This modality is to use the brainwave to control robot. There's other modality. We can use the voice, use the gestures, use the haptic approach to control the robot. The brainwave-based approach is not to replace the other modality, but as an additional modality to control them. Sometimes we can combine different modalities together to increase reliability, because sometimes other modality may not work. Think about a more noisy environment. The voice-based approach may not be reliable. If we doing job, we cannot use the hand to make gestures because our hands are occupied and so on. In those cases, we can use a brainwave-based approach. Another novelty in this research is micro robot control strategy. This also identified as the challenges listed in the red bullet here. One reason for this is because we cannot retrieve accurate brainwaves. This is a remaining challenge. Stability is another one. Over time, our thoughts may change. Our brainwave is altered. Whenever we blink our eyes, the signals are contaminated. Or there's a coworkers pass by, it's disturbing ourselves. The brainwave is not stable. And fine-tuned, fine-grained control command is very difficult to get. These are the remaining challenges. As another example, challenges is how to collect a signal, brainwave signal, when we are doing normal tasks. In the recorded demo, you see the operator, when issuing a control command, he is standing still because he cannot do anything else. Otherwise, the signal is not pure or contaminated. That's the challenge. We consider to use different training or learning algorithm, try to separate the complex brainwaves, try to identify the hidden pattern, even if in the future we normally do our daily tasks, still can separate and retrieve, capture the true control command. how to do that is a research challenge. The last one is our mental status. If we can use this properly, it can be used for different purpose as well. Here, if you look at the diagram, the brain, we can monitor the situation, and the robot is to control the action. By checking the engagement level, we can properly arrange the task execution. For example, the tiredness level goes up, the speed can go down to adjust accordingly without hurting the operator for safety reasons. Another safety concern is we check the panic level of a human. If there's suddenly a surge in the brainwave signal in high frequency, that means the operator has been pose a risk to the operator, generate a panic signal, then we can trigger the emergency stop. In the future, there's other ways to collect sensor data. We use a non-invasive approach, just to put sensor electrode on the surface of skin. But if I use this invasive approach, like the link from Neuralink, it has 1024 electrode. It can retrieve more accurate data and high quality and high amount. This can be the future research direction as well. But right now, this is not ethical to do surgery for the operator for students, not possible. So I stop here. There's a little bit of time, but this time can be used for later Q&A session. Thank you very much.
So thank you so much for that really very visionary and promising research. Quite interesting. Mind reading, I see in the future. I'm not sure how well we as humans actually read the cues of others. So it's interesting to tie it more directly to the brain. And certainly I can see many other applications well beyond manufacturing, such as assistive technologies, where individuals have limited motor skills, and to be able to interact and control their environment directly would be amazing, actually. So thank you very much for that very pioneering presentation, Dr. Wang. Okay, so the next presenter that we have is Dr. Costa. If you would like to go ahead and get started.
Good morning, afternoon, night, everyone, depending on where you are. It's a pleasure to be here. And my name is Paulo Costa. I am with George Mason University. I'm here. I'm part of the Systems Engineering Operations Research Department, and I'm also director of the C4I and Cyber Center. So today I'll be talking more about the research that I do in Cybersecurity Manufacturing Innovation Institute, CyMINI. So this is an initiative from the United States government, Department of Energy. And it's an institute that comprises a number of partners, including universities, national labs, and also industry partners, as I will show further. So the research I do there, I'm actually vice president for security and automation and supply chain security, is really related to the topic of this presentation. So it's a rather long title, so I will not repeat, but basically what I want to convince you today is that one of the main obstacles that we have today for a larger adoption of advanced manufacturing database oriented smart manufacturing is really the establishment of a return of investment, meaning how can I justify the costs of implementing sensors in my production line, even knowing that with those sensors, I'm becoming more vulnerable. So that would be basically my main focus for this talk. So just to have the understanding correct. When I say advanced manufacturing, I'm looking at the more broad aspect of this. So, I mean, when I was thinking on how do I present that, I look at, there is a number of metrics that you can find in the internet, doing some research. I just picked these report from Deloitte that basically shows and compares what can be done. I mean, compares advanced manufacturers with non-advanced manufacturing. So the productivity, according to this study, is impressive. I mean, it's 9 times more than productive than 10 years ago. So basically, on average, when you apply advanced manufacturing techniques, you double the productivity of one person. And of course, I could have shown other type of metrics, but they tell the same story. It's a good thing to do. It's something that will save you money and make you more competitive in your industry. So the whole talk really focus on this, focus on explaining the advanced manufacturing, the digitalization, I would call that way, as the way forward to be more efficient, which is all that we want. But the digital transformation, I mean, adding sensors, adding data collection to your manufacturing and supply chain creates new and expanded cyber attack surface. So you become more vulnerable. And also current cybersecurity approaches tend to be piecemealed. I mean, you cherry pick a few that do not really cover the whole idea. They tend to be underutilized and also ineffective. So as a result, it's not a business model that can be sustainable. As we could see, if you browse the literature 10 years ago, even 20 years ago, all predicted a very fast adoption of advanced manufacturing techniques, of the sensor-based data-intensive applications in manufacturing and in supply chain. That's not what we've been seeing. I mean, there was progress, of course, but not as much as we would expect. And I would mention that, I would argue that this is one of the main causes. I mean, the lack of a sustainable business model. So to illustrate that, that we are close and to get then we need a more digitalized manufacturing supply chain approach. I would show ask your attention to the 2 graphs on the right of this picture. So what you see in the first one on the top is energy consumption. When you look at the manufacturing part, you see 27%. So 100% here means all the energy consumption in the US. I think this was 2015, I might be wrong, but that was equivalent of 100 quadrillion BTUs. So that was the whole US consumption, and 27% was due to manufacturing. But when you look at the cyber attacks, that very same industry that uses 27% of the US energy is responsible for 35% of the attacks. So it's an easy target. It's a very seek after target, because usually the hackers can inflict a lot of damage and get money from that. And that's basically what we see in the news when you look at the attacks against the manufacturing supply chain infrastructure. So the key thing is the digitalization is coming, and it's going slower than we think, but it's coming. And what happens is, if it's not done right, it really defeats the purpose at this point. I've seen a number of examples of, especially in the small companies, because they don't have the same assets that a large company has. They see protecting the infrastructure as a cost. They can't see the benefit on this, and as a result, they avoid, and they get attacked, and then they get ransomware or something like this. They have to spend a lot of money to as a result, and that's only when they realize, oh my, I should have spent that money. So as an example here, of energy, you can see that one case study is the aluminum engine block production. So it consumes only the machinery for that consumes 7.5 million kilowatt hour per year. So if we digitalize this, meaning if we put sensors in optimization algorithms, we use machine learning techniques, use AI, we can save 0.75 per year. And if you also act on vibration minimization, also as a result of knowing more about your machine function with sensors, of course, you can save an additional 1.875. So I think this tells the story that a lot can be done in terms of efficiency by adding sensors and adopting the data-intensive techniques that we know. However, the problem of cyber attacks because of the extra vulnerability is indeed something that we cannot ignore. So as a response, the US DOE created an innovation institute, the Cybersecurity Manufacturing Innovation Institute. What you see here in this in this slide is there are 4 tiers of partnership, and all these institutions are there. You can see that is the last time we saw it was 59 members, 3 of which are national labs, and we have a number of industry leaders and universities as well. So it's a very large effort and aimed at manufacturing. So you can have more information at www.Symany.org. So Symany, when it was created, it has these goals for 5 years. 1 quad saving of energy. 1 quad, as I mentioned, is 1 quadrillion BTUs. It's a 1% of the US energy, which is a lot. So even 1% is a large amount of money. Reduce cyber vulnerabilities by 1 trillion, having 1 million workers in on the advanced manufacturing industry trained in cybersecurity, and a $20 billion saving over 5 years. So that's very ambitious. So to show that we can actually perform and do that, I'll just go over this slide. It seems complex, but it's not as complex as you see. If you look at the columns, each column here focus on one specific area. And by the way, this is all the data that you see here are based on studies that were conducted independently, although with the support from DOE. So in the columns you see, for example, let me pick this one here, petroleum refining. The energy consumption of the petroleum refining in 1 year in the US is 4.7 quadrillion, so quads. The improvement that can be done with digitalization without being attacked, it's a 1.4, basically 25%, right? The market penetration that we estimate is actually 8%. So if you take 8% of 1.4, you get this number, 0.083 quad. When you add across these sectors, you see then in 5 years, we reaching that number of 1 quad of energy savings. The way to do that is really working on a new perspective. So everybody is familiar with the metering, measurement, and verification approach, right? So you, the original MNV, you have different options, option A, B, C, if you remember that. Basically, you have different ways in which you isolate, measure, and verify how efficient you are. Well, that was an old concept that is now superseded by the MNV 2.0 that basically automates this and makes the smarter metering based, and that's becoming reality in most places. What we have been working in Symany is the cyber security, energy, and emissions quantification framework. So it's not that we are creating new sensors, we are establishing a framework that allows the introduction of advanced sensors in a much more secure way. So what you have is this secure IoT-based real-time analytics and anomaly detection. And we call this intelligent efficiency, is really trying to implement the techniques that we already have in a framework that would allow you to be a lot more conscious on what you're doing. And I would argue again that this lack of a structured approach to implement M&V 2.0, 3.0, wherever you see there's 4.0, there's many competing acronyms there. It's not the technology only. It is really how you implement it. Is the human factor, is the cybersecurity factor. All them have to be counted in order to produce a valuable result. And that's basically the goal of the SEEK framework. Okay, I definitely do not have time to go through this. The idea here is really to go back to that petroleum and explain how the 0.82 in 5 years can be achieved. So I will only focus on a few aspects. You see, for example, this one objective, of course, is to show that it's a complex environment. We don't want to dumb down the sectors. Each one has a high level of complexity, many things happening in parallel depending on a number of factors. So the studies that supported what I showed before actually took all these into consideration. So you have to think on a number of details. For example, here in the petroleum industry, you have in horizontal axis, you have different ways in which you can use the crude distillation of petroleum. So you have, for example, hydrotreating, isomerization, and the expectation here is that we can save 44% based on the assumptions here that you see below. Near term is 3 years, mid to long term is 3 to 7 years, and more than 7 years is long term. So the considering this time frame, I was not part of this study, but basically it was understood that 44% can be saved in the isomerization. And of course, in the whole linear workflow here, it will be a smaller number, but when you add in each one of the horizontal axes, you will reach that number here. For now, I'll just ask you to believe me that this was calculated correctly. But the main goal here is really to show you that the studies that the OE conducted really paid attention to a number of details in each one of those sectors. So the key technologies, use of for the process control, use of neural networks, knowledge-based systems, blockchain technologies, not only to improve the process control, but also to have traceability and a little bit more of a resilience against attacks. Process optimization integration, analytical tools, site integration, cross-cutting technologies such as fouling minimization. And so I think my point here is really that a number of technologies that were considered are already there, already ready. Implementing them is not so easy because of a number of constraints, and that's one of the goals for the SEEK approach to make this possible. So I want to go back to the assessment that I talked about, the approaches being piecemeal, underutilized, and ineffective. So the question to be answered here is why manufacturers do not implement the modeling, the measurement and verification tools in a proper way, in a secure way. So basically, well, number one they're not fully aware. They don't know the vulnerabilities and associated risks. They just look at the technology, oh, it can improve, let me implement. And then they try to make it secure by putting an antivirus or something like this. So awareness is a big deal. Awareness is a major problem that we see in the industry at this point. The number two here, not know how to reduce the risk. So even the companies who got attacked by I mean, I've seen myself companies having successful attacks being deployed against them and causing them then a lot of damage. So ransomware tends to be very common on those cases, and you get to the email of a supervisor, and then you escalate, and 2-3 months later you can do a full attack in the factory. So that is very common. But even after that, they do not know how to reduce the risks. Yes, I was attacked. How can I improve? So that's another issue. They also they lack control over the risk and exposure. So they don't really, they see a sea of offerings in terms of solutions. Offerings that are not compatible a lot of times, or they are overlapping, so you're spending more money than you need to address the same type of problems, while some of the problems are not addressed. So this is another issue that we see a lot. Number 4 here, because there are no holistic solutions. And I think that is basically a result of all the other 3 that I mentioned. You don't have a way to, and when I say holistic, it's not that we're using all the products from the same manufacturer. No, it's the other way around. We want to have diversity in terms of what you are acquiring, in terms of sensors, in terms of security measures, but at the same time, all of them should be compatible. And basically, this doesn't happen. We don't have strong standards in this industry at this point. And finally, security automation is costly. I mean, it's money. You spend money adding sensors just to realize that, oh, now I have to spend more money to integrate the sensors, to use the data that the sensors acquire, and to make them more secure. So these are all things that are in front of the manufacturers and prevent them to actually make decisions. And that's why we believe in this point that having a clear-cut return on investment that shows, if you do this, here's what you got, and so on, here's the options, is what really should drive the decisions of the manufacturers. So right now, I think this is more of a summary slide. So basically, what we see currently with all the technology that we have in terms of sensors and measurement verification techniques is really, at this point, lack of advanced applications for intelligent manufacturing. So there's not a lot of integration. The intelligent side of manufacturing is growing a lot faster than the applications available for it are. Also, emphasizing here the lack of a formal cybersecurity architecture, one that is based on standards and that can be applied to, you don't get vendor locked. You have many solutions that you can implement according to your case study. Inability to track, so traceability of energy efficiency savings means you are buying sensors, you implement securely, but you don't know how much you're gaining from it. So you don't know whether your investment really paid off or not. So your decision making is compromised at this point because you don't know how much worth for you to invest on those technologies. So how we attack that? Basically, we increase the application in intelligent manufacture of smart measurement and verification by enhancing the data processing capabilities. In Cymene, we have a whole sector just doing research on how to integrate different techniques in a way that is not costly. And all these research will be, of course, available to our partners and to everybody else. Bring a structured way of developing, deploying, and evaluating. So that's the area actually that I work in Cymene. So figuring out how can we structure, how can we be controlling the whole life cycle of the implementation of intelligent manufacturing for the supply chains and the manufacturing itself. And finally, because it's a DOE project, right? It's capturing the embodied energy. So for each product that goes outside, I mean, that this result of my manufacturing, whatever my manufacturing is, whatever my supply chain is, I can tell how much energy was spent to produce that specific product. You can only do that. You can do that using the technology that we have today, but you can only do that in a feasible manner by having a structured way of implementing this. And that's basically what we've been trying to achieve in Simane. Okay, so this is, I think, my last more complex slide. I just want to illustrate to you how we calculate the ROI. What are the techniques? What are the things that we've been developing there to be able to calculate, to enable decision makers to know how much they gain by investing in those technologies. So the process, it's agnostic to the industry, the sector. So we start, what you see in the left side, establishing the baseline. And when you say establish the baseline, you see that is in two different dimensions. In the energy layer, that basically we want to know, we want to have models that can calculate precisely the current energy usage. So we have been adopting machine learning techniques, regression analysis, nothing that is not available today. It's just that we are doing in a structured way to learn how much a given sector is producing, is not producing, is actually using in terms of energy to produce its goods. Keep the production level in mind. So we want a model that is dynamic enough so I can vary production and see the impact on the energy consumption. The next layer that you see in blue is really one of the most difficult for us, which is to assess the current performance in terms of cyber, calculating the risk. So we've been adopting techniques for looking at attack data from the past in that specific sector and using different techniques to assess the risk. And that is not as trivial as it might sound. Figuring out how to calculate risk is one of the main issues in the baseline. Once you establish the baseline, and that graph is just notional, you basically have a factor of how your cost changes based on time in terms of energy consumption and in terms of risk as well. Well, then the next phase is really to improve that, is really having ways in which you can enhance your baseline. So, of course, you see adopting IoT devices to give you more data about your process so you understand them more, smart sensors, and then use what we call here optimization modeling. So we have both macro models that go at the level of each specific machine, robot being in the factory line or in the supply chain, all the way to the higher model so that was a micro model, sorry. The macro model takes all these aggregates and gives you a picture of how much you are saving by employing these techniques. Same thing in terms of cyber. How you mitigate existing cyber threats, how you reduce them. So we use a digital passport, digital bombs, and a number of techniques that are already there, but we want to make them more easily available and not needing a degree in cybersecurity to understand and use it. So that's the main goal for that one. So the result of this improved planning is that we now have a projected usage. The cost will go down if you apply that. Well, then you add the cost for implementation. So here's how I can reduce based on the technologies that I added. But then when I insert the cost of implementing those technologies and the extra risk, that's what you see here in this other line. That's the aggregate cost risk analysis. So you do that basically analyzing the implementation costs, device acquisition, personnel development, how much training is needed, assessing the risks of in savings plan, what can go wrong here, and so on. And same thing applies to cyber. So at the end of this process, you will see that this increased here. And we test many different scenarios for that, an optimistic scenario, pessimistic scenario, and an average scenario. If you're happy with that, you go to the next. If you're not, go back to the drawing board, do it again, see what can be improved, and repeat. So we iterate this process a number of times. When you're happy with this, then you go to the energy realization and savings, where you are happy with this curve here. And of course, you do a projection of how it would have been if you just keep the status quo. And that difference is the ROI. So the savings that you have here is really the return of investment. Of course, this was a more high-level view of the processes that we do. There's a lot of details that I do not have the time to go through. But I think the important part is that what we provide is really a structured way to make a clear ROI visible for a number of different approaches that you can see. And now, with that in mind, you can make a much wiser decision depending on your assets, depending on your goals, and what you can do. So you will not see the implementation of security IoTs in your supply chain as a cost. You will see the benefits, and you see that in a much more structured way. So that's basically how we've been developing things in Symantec there. As a summary here, I would say we can improve energy efficiency with integrated and secure automation, supply chains, and people. Symantec doesn't only look at technologies. It's really a systems engineering approach where we see the big picture, all the interactions between the algorithms, what the data is needed. Do I really need that sensor? Where do I put the sensors? How AI can help me on how many and where to put the development, the deployment of those sensors. Once I get the data, how can I utilize? What are the best techniques given the data I'm having? How does that progresses in time? All these things have been studied there. We cannot stop attacks. They will happen. The key thing is being ready for them when that's the case. And finally, I think the key thing here is to reach great protection as a faster rate of implementation of those techniques. I think overall, the whole industry can benefit from there. So thank you for your attention. I'm sorry I probably spent more time than I should, but I think this is a key problem that we have, and I'm glad that I was able to come here to talk about it. Thanks.
Thank you so much, Dr. Costa. That's very insightful. It's wonderful that there's an institute and researchers, including yourself, advancing this area. It's going to be obviously key to bringing more manufacturers into the integrated world of smart, intelligent manufacturing for this adoption to address this key problem. I also personally appreciate the identification of not only the challenges, but the opportunities, and look for additional research by many across the nation and indeed across the world in this area. Our next presenter is Dr. Pakit, so I'll turn this over to you. And as a reminder, please feel free as we go through the presentations for our participants to be typing questions into the Q&A section.
Thanks, Janice. So good morning, I'm Vincent Paki. I'm the section head of Secure and Digital Manufacturing. And I'm going to go over a presentation that's going to discuss the use of artificial intelligence and machine learning for improving additive manufacturing processes. So I'm working at the Oak Ridge National Lab at the Manufacturing Demonstration Facility, which is a very large building where we have about 100 advanced manufacturing systems. So they cover additive manufacturing, carbon fiber production, material characterization, intelligent machining, robotic and automation, and so on. And my role over there is to focus on everything that has to do about data science. You have at the bottom of this slide a link if you want to take a virtual tour of the facility. But the idea of this environment is to explore advanced manufacturing technologies for the production of the next generation components. And my job here is to look at collecting as much data as possible around those manufacturing processes in order to understand how they operate and how we can force them to achieve certain objectives. So the role of my section really is to build the data science that will be able to connect the dots between the structure, the properties, the processing, and the performance of those different particular systems. So they are all very complex in nature. And so the idea is, if you're observing, if you're collecting data around those manufacturing processes, you're going to be able to get a better understanding of your particular processes. And if you have this level of understanding of your system, you're going to be able to start developing the new techniques, the new technologies that are going to be helping you optimize such process toward your particular goals. Sometimes you're going to have like something that's going to be manufactured according to a particular plan, but this plan will go probably wrong, and there are going to be the need to implement correction mechanism and feedback loop control processes in order to ensure the final outcome. So that's going to be another like way to act on the machine, to decide on how the machine should behave in order to change something that was not going according to plan. When you will be in control of your understanding of the process, the optimization of this process, and the control of the machine itself, it's going to become a lot easier for you to tell that you're going to be able to, you've been able to achieve the production of the component that you wanted, and therefore defining the techniques and the methodologies to certify and qualify those particular components are going to be a lot easier for you. So why is additive manufacturing or advanced manufacturing a challenge? And so every time I look at one of the systems we have in the facility, I look at every single of the components we are producing as a massive Lego set. Okay, so you have an example here of a Millennium Falcon with like very nice tires that are all of the same color, placed correctly, and so on, because you had someone going through the development of a process that is documented in a manual, providing you with the right pieces in order to put together this object, right? And this is the way we are building something in 3D using an additive system or a subtractive system. The problem you have is every time you're actually running something out of those machines, you're running a small experiment. Each new tile is a new experiment on its own. And ultimately, this is what you're going to get. You're going to get something that looks like a Millennium Falcon, but that does not have the actual quality of it. And this is exactly what you're seeing with any of the components we are producing. If you do not understand what you're doing with your process, you're going to be able to produce something that looks like what you want, but that's not going to be able to perform the way you want ultimately. But one of the key advantages of advanced manufacturing technologies is that you can observe the manufacturing process at any given time. And I have a few examples here. So for example, I'm going to be playing those videos in sequence. You have here a video of an electron beam melting process where imaging the surface of the powder bed system, of the manufacturing system, using a thermal camera, you're going to be able to look at thermal conditions during the manufacturing process. If you're moving to visible data, you're going to be able to observe what's going on, and you're going to be able to see, like in this video, like smoke and spatter particles and events that are occurring during the manufacturing process that can be tied to some of the quality issues you may encounter. If you do this with composites, same thing. You're going to be able to observe the deposition of like plastics and see if there's like anything that goes against your original plan. Machining is the same way. And if you start like making this even more complex with the addition of more robotic systems, like the one you're seeing at the bottom right of this slide, you're going to see the coordination of multiple manufacturing technologies that produce the same components. So there is this need of being able to observe how the coordination of equipment can actually achieve the ultimate goal you have. So you can observe things. So in order to do that, you're going to be looking at your machine and place sensors. In this case, I'm going to be focusing on camera, on imaging sensors, just because it's easier to visualize, but you can use anything you want. You can use acoustic, you can use like power measurement, thermal measurements, and so on, but cameras are sometimes easier to understand. So if you put a camera on the top of your machine looking down, you're going to get an image that looks like this, okay? If you zoom in, you're going to be able to observe particular features, texture features that correspond to what happened during your manufacturing process. Where AI comes into play is those images can be sizable, and it takes time to annotate every single pixel and flag them based on the type of defects of anomaly you're detected. So if you are focusing just on porosity, this is what a close view of an in situ data set will look like, where you can see those white dots. The AI will map out all of this for you automatically. If you do this on a per layer basis, what's interesting is you can stack that up over the Z height of your component, and now you can have like a full 3D map of the defects present in your geometry. This is done in situ, meaning you are manufacturing your component, and next to it, you are actually building this data set that provides you this type of information. What's interesting is when you start comparing this particular cylinder, and you're trying to map out inside it the different defects using a X-ray CT, X-ray computed tomography system, and you compare this to the mapping you've done in situ. If you compare the two, the green and the reds are showing you the position of pores present in this geometry. At the difference of resolution between the two techniques, you can see there is a match between the two. So that's where being able to instrument the system, observing what's going on, and using AI in order to detect this defect can actually provide you the information you need about the quality of the component way before you're done with your manufacturing process. Porosities are one thing, but you have like other type of techniques that can, other type of defects or features that can correlate to particular defects down the road. So you have, for example, for one type of manufacturing technology, laser powder bed fusion, you have different type of images like tiles that are showing you certain texture features that are very specific of swelling in this case, recorder hopping. For just to give an example, electron beam melting, you'll be able to see the pores that we saw earlier. You might be able to see crack and bowling and other type of thing that you can observe things. You can observe what's going on with your process. Same thing with binder jetting, which is another type of manufacturing technology. But those are multiple classes of defects, and this is a perfect scenario for using AI in terms of automating the detection of such defects. For that, we've developed at Oak Ridge, but there are like multiple other options around the research community, where if you take an input image like this and you annotate your images based on the type of features you want to detect, you can train a neural network model, most of the time, conventional neural network architecture, that will be able to take this, excuse me, take this image or multiple images as an input, move through the network, and then start like creating like a map of all the defects present in this particular layer. Going back to my previous slide, if you stack that up over the Z height of your component, now you can have like a full 3D represent of your geometry and the map of all the different features and anomalies that are present in there. So this is a direct assessment of what you will be able to observe. Now, there is not necessarily a direct correlation between what you observe and what you actually are going to get in terms of material properties and the type of performance of the component you will get. What you want to do is start using what we call a digital twin of the component. And going back to my earlier slide where I was mentioning the idea of a Lego set, we will be looking at every single component we are producing as a massive Lego set of information. So on this slide, you have a turbine blade. I'm going to show you more in detail in a second, where each location in space can be considered as being a filing cabinet, where in this filing cabinet, you're going to be putting data that correspond to the different data streams you're going to be collecting along the production of your particular component. They can come from modeling and simulation, from intent, in situ monitoring, that will be the images that you saw earlier, but also ex situ data, and that could be some of the CT information, computed tomography information, or any type of microscopy data and so on. If you structure your data set the same way, now you're going to have a digital package that is a digital clone of your physical component. And this digital clone or digital twin will follow this structure, which will create a unified data architecture, which is ideal in order to have an abstraction of the type of geometries, the size of it, and the type of material being used. At this point, you're going to have just a data package, and you can do anything you want that is listed on the right-hand side of this slide in terms of processing such data for the understanding and control of your manufacturing process. So As an illustration, this is what it will boils down to. So you have like this turbine blade in the middle. This is the physical component. This is my digital representation. I'm storing data in this filing cabinet. And what I'm going to do, I'm going to look at multiple variables, and I'm going to change the color of those particular voxels or those small blocks based on the value of the variable I'm trying to represent. So in this particular case, I have 9 variables, okay? The minimum value of the variable will be represented in dark blue. The maximum value of this same variable will be represented in dark red. So if I change the color of my digital twin, and I change the color of those voxels based on the value of the variable, I can start seeing gradients. I can start seeing changes, drastic changes within my component that are representative of something that happened during the manufacturing process. What's interesting is now when you combine them all together, you're going to be able to map out in any given location within your geometry certain signatures of what you will expect being like a good signature of a good portion of the component. So it can be very punctual, it can be like entire regions and so on. But what you'll be able to do also is identify those anomalies and those signatures that are very different within your component. So now your digital twin and all the data you're going to be collecting can be used to train a neural network to automatically detect those particular anomalies and map them into space. And so now you're going to be able to find automatically correlations between what you tried to do, what you actually did during the manufacturing process, and what you obtained. And so you're going to be using this to your advantage in order to start driving some of the controls on the manufacturing process. So in order to do that, you need to complete the loop. You need to have data from any given steps. You need to have data from your intent. You need data from your manufacturing process, and you need to have data on your actual material properties outcome. A little bit more technical on this slide, but I'm trying to keep it as easy as possible. The idea here is for us to produce data set that can cover the entire parameter space of the machine, which is required for any kind of artificial intelligence and machine learning techniques. You cannot just learn from good stuff. You need to learn from like failures as well. And so in this particular example, you have 2 builds. They are identical in their geometries. You have cylinders, you have like thin wall structures, you have like blocks and so on. The only difference is coming from the process parameters we're going to be using. So this image at the bottom is a cross-section across the geometry, where you can see those big blocks and the cylinders. Green means that I printed the entire geometry with the same set of process parameters. So everything should be identical everywhere in the geometry. On the second one, instead of printing with the same type of process parameters, represented with 4 colors, I use 4 sets of process parameters. This one is a good set. This one is the better set. This one is a set that's going to produce anomaly 1. And this one is the set that's going to produce anomaly 2. Now, if I produce digital twins for those 4 quadrants that produce good data and bad data, I can start like mapping this out with any of the other data collected on the machine. And now I have like a very nice data set. I have a nice digital twin of my components. Now, I'm going to take those blocks and I'm going to cut them into small samples here. Those samples are going to be tested, and the test here is just we are going to be pulling on the sample, it's going to break, and based on how it breaks, that's going to give us a quality score on this region of the geometry. I can map that out over the cross-section of my geometry, which means I can connect the dot now between my in-situ data package and the ex-situ testing and characterization of the component. And in this particular case, I'm focusing on one particular test, which is the ultimate tensile test, strength, where the minimum value is like this purple-ish color, and this one, the yellow, will be the maximum value. If you look at this overall, it looks like I have like yellows everywhere, except here where I have blue. So now I have to figure out why I have something that's good mainly everywhere, but there is like something bad in a particular region of the component. So back to my Lego set, I map out my data at the gauge section, which is the region where the failure will occur. I have my characterization data, which is the actual curve that you're going to get from the test. And I can start training an AI model that can start predicting on its own what will be the actual outcome of the test. And that's what we are seeing with this scatter plot. So you have the ground truth at the bottom, which is the result of the test that we perform. and the y-axis will be the predicted results just using the data we are collecting. In this particular case, the prediction is just based on the in situ observation. So the model that was trained, the AI model that was trained, capture a lot more information along the way. But the only input I want is an observation during manufacturing, and I want this observation to tell me what will be the quality of the component. Because it's a scatter plot, what you want is to be on this dashed line in the middle. The closer you are from the dashed line, the better you are with your prediction. So what you can see here, if you ignore like the few outliers that we have there, you have like a nice cluster here and another cluster, but it is not as nice. If you were to put like a line at 450 MPas, this is the limit between a good and a bad test. So a bad test will be on the left, a good test will be on the right. So the model is able to predict only in situ data pretty accurately what will be the result of a mechanical test. Okay. The second cluster here, still the model will predict that the test will be bad. However, it cannot predict how bad you're going to be. But the takeaway from this is it is possible to use some of the data you're collecting during the manufacturing process in order to predict what will be the performance of your component, which is what you want ultimately out of any of the work you're doing using in situ monitoring. So from this discrete observation, which is the traditional way you're going to be characterizing the component you're producing, you can start like predicting over the entire geometry of your component. This is just represented on a single layer, but you can do that over the entire 3D block. And that's what you want to do. You want to be able to tell every single of the blocks, every single of the Lego blocks I use for my Lego set is actually what it's supposed to be. And instead of having my multicolor Millennium Falcon, now I know I have like all gray and nice looking component, which is what I want ultimately. So now you can start like using this to your advantage for various things. So if you were to print a geometry like this one, and with cylinders at the bottom and cylinders at the top, those cylinders, if you use an uncontrolled environment, you're going to be printing those cylinders under different conditions. If you excise material micrograph, which is like a microscope image of the grains that compose this particular those particular cylinders, you're going to see different type of grain size and grain distribution and so on, which means that your cylinders, they will look cylindrical, but they will not perform the same way if you were to like put pressure on them or else. One of them may break faster than the other, and that's the problem we have with additive manufacturing. However, with all the data you've collected, you will be able to connect the dot between the manufacturing process and those manufacturing outcomes, and then train a neural network architecture that will feed the objective as an input and will spit out the new recipe on how to manufacture those components. And now you're going to be tailoring how you're going to be manufacturing those particular cylinders based on where they are located in the geometry. And if you run the same experiment with like a customized set of process parameters over the Z height of your component here, you're going to have now microstructures that are going to be looking a lot more the same. And so this is you taking over the control of your particular machine. Now, as a final example, I'm going to show you how clever you can be with those manufacturing processes and where some of those challenges will lie in the near future. So if you were to print a particular geometry like this is how you're going to be printing your particular layer. Those colors that are showing up, those lines of colors, are going to be the lines you're going to be using printing in order to melt this particular cross-section. When you're printing lines like this, you are never in control of your thermal conditions. So you're going to be melting your material, going from solid to liquid and back to solid, using a very uncontrolled mechanisms that will lead to orientation of the crystals, the size of the crystal we saw on the previous slide, that will be all over the place. So you're going to be producing your multicolor Millennium Falcon here. If you want to change this, what you want to do is instead printing dots. And if you print those dots at at particular locations using a particular sequence, then you're going to be able to control locally how those solidification rates, how this passage from liquid to solid will occur. So as a demonstration, what we wanted to do was to print a portrait of Mona Lisa, where we wanted to have a particular type of grain for everything that is white in this image, and other type of grains for everything that is black in the image. So for that, instead of printing lines, we printed a series of dots. And you can see there is an infill, there is like a background set of points that are being melted. And this is us going over like 60,000 points total. We can observe all of this. So when you're putting like a high-speed thermal camera, you can actually observe the printing process, because we were doing it like one layer after the other. That's why the portrait was already present, but we were like changing the microstructure anyway. If you look at take a top picture of the sample, this is what it's going to look like. And ultimately, what you're going to be able to do is put this in a machine that will provide you a map of the grain orientation that you have in your particular sample in the form of a representation of color. And as you can see, the portrait of Mona Lisa that was black and white is now like a dominance of green and red, which means that we were able to change the orientation of those grains using the process parameters. What that means here is you now are not manufacturing a component, you are manufacturing material properties and material performance in space. And this is the holy grail of metallurgy right there. And this is all achieved using a lot of data and a lot of artificial intelligence. The 60,000 points problem that you have here is a traveling salesman problem. Well-known problem, solved multiple times, except in this particular case, your objective function is not optimizing time, it's optimizing an entire map burning, and you want to be able to control how this map is going to burn and burn down. And so this becomes a lot more difficult, because now every time you have like a solution for those 60,000 points, you need to run a full-scale physics-based model of the entire layer in order to come up with the actual set of points that you want to, series of points that you want to make. So a lot of AI for the optimization, a lot of the AI for the replacement of the modeling and simulation packages, a lot of the AI for some of the controls and how you're going to be like shaping the actual file that will be fed to the system. So with all of that, there are still a lot of challenges. With the example I gave you are just like preliminary results in a lot of areas. So what we're going to have to start doing, and this is my last slide here, is to focus on defining what a digital twin of a component is. What is the information that we need to have in order to be able to understand how a machine, how a process occurs with a particular system. This will require to build also a very large database for advanced manufacturing. So all of this data will have to go somewhere, and it's going to be have to be a collective endeavor in order to get to producing a data set of magnitude that will let you train the AI model that can work for your particular application, but can also be interpreted and explained, because this is going to be also one of the key elements. Everybody is saying like AI is going to revolutionize everything, unless we can trust any of the AI models we are developing. There is nothing that's going to be revolutionary about all of this process. Augmented manufacturing workforce. All of this will have to go to some operators of the machines. They don't have a PhD in computer science. They probably don't even know what a neural network is, but they're going to have to be able to work with some of those techniques, some of those advanced techniques, and being able to provide them this knowledge in a way they can understand and act on their manufacturing strategies will be very important. For that to happen, we also need to work on sensing and measurement technologies. Most of the systems we are working with right now, they are blind. They don't have adequate sensing modalities that can provide the understanding of what's going on. So we're going to have to develop new sensing modalities. We are going to have to instrument machines in such a way that they actually provide the information we need for anything that is related to data science. And all of this will have to run at the edge. So there are going to be a lot of work around edge devices, IoTs, and communication between systems, which goes back to some of the previous talks that we're discussing, like interaction between the operator and the machine, the cybersecurity aspect of everything we do. And so all of this will have to be like a key research areas in the near future for advanced manufacturing. And with that, I'm going to end my presentation and jump in with the questions.
Wonderful. Thank you so much. so many opportunities about how AI and machine learning data analytics is key to the many advances for process quality and control, and links with digital twin and really the future, many opportunities. So now what I would like to do is open this up for question and answer. Please type your questions in the Q&A box, and I'm going to turn it over to Dr. Salvi to help us go through it. So my suggestion is to read the question and have one of our panelists answer that, please.
You know, to kick things off here, I think something that's pretty interesting is the intersection between Dr. Paula's work and Dr. Vincent's work. You see a lot of intersection between the sensor modalities, what can be detected on a system, what is or what is not being detected on a system, and preventing malicious use of that. I mean, clearly there's overlaps here. I'd kick it over to you to see where you think the next steps are. Where's the easy way to get integrated in this, and where's the long-term vision of where you see this intersection going?
So your question is for?
Did you get both Vincent and Paula's perspectives on this? You know, one from a sensor side, one from the cybersecurity side, and see what the long-term vision is of overlapping, as well as the near-term next steps.
I'm gonna probably answer your question, and at the same time answer Andreas Linos' question in the chat, where he asked, well, what type of part metrology can you perform in situ? So a lot of the instrumentation that is required on those particular systems will be driven by some of the scientific questions that are that need to be answered. And so I presented here like camera measurements, camera-based measurements here, just because it's visual, people understand this, but the main drivers really are what are you trying to achieve, and based on what your target is going to define the type of measurement you're going to need for your particular system. Some of those systems operate at low temperature, some operate at high temperature, and it has an impact on the type of information you're going to want to collect. So based on that, there are going to be a drive towards defining the suite of sensors that need to be integrated into those machines. And the opportunity really is to start convincing some of the manufacturers of those machines that they need to start adding some of those sensors on their system, so that way we can start like seeing what's going on. Because most of the time they do not provide any kind of sensing modalities, because they don't necessarily want us to see what's going on during the manufacturing process. And that's one of those challenges, and that's one of those opportunities where we can actually have an impact. We need to provide some confidence in the sensing modalities we are going to be suggesting, and explain why there is a business case on using them for any particular application. So maybe to expand a bit on Andreas' question, what type of part metrology you can perform in situ? You can perform a lot of things, a lot of measurements in situ, but that's going to be really based on what you want to get. In some cases, some of those sensors will not work, however. Like we have to be clear. There are things that you can't do, and that's going to be just based on physics most of the time. But it's all going to be based on ultimately what you want to be able to detect. If what matters to you is to detect pores of a millimeter in size, that's going to define the type of sensing modalities you're going to be looking at. If you want to detect them at very high speed, that's going to be defining how you want to instrument your machine. So probably like a long-winded answer to both your question and Andres, but I want to just say that it's not a solved problem. We still have a lot of options, a lot of opportunities to explore this particular space, and I highly encourage people to start like trying things and see what they can actually observe during those manufacturing processes.
Yeah, fantastic answer. So let me now kick this over to Paul, a little bit of a modification. You mentioned something interesting that, well, most people don't want you to see what's going on in their systems. So you've almost either got to blow the doors wide open, see everything, and have complete trust, or have zero trust whatsoever. So how does that fit into a cybersecurity framework in today's day and age?
Yeah, I mean, I think I will start by emphasizing what Vincent mentioned, because for us, it is really dependent on the application. So for example, in some, you do have a lot of metrology already built in. So for example, chip manufacturing, it's already there. So for us, it was actually difficult to implement, oh, I will add sensors. You don't need, the sensors are already there. How to capture the data and make it exposable to, as you alluded to, Kyle, in terms of how to pass the data to the algorithms or to whoever is doing the calculations in a way that doesn't make it vulnerable. It's a different story. Others, no, you have basically to, so for example, anything that uses more power, like an oven for ceramic products, where you have the ceramic, you put a coat and you have to pass through an oven. Most of those machines are electric powered, but do not have, so by being electric powered, you have, I mean, control over how much energy you can put. But I've seen a lot of these setups with basically no metrology. I mean, they just have like 2 or 3 options in the machine, and you can't really do much. In those cases, we have the option to add some sensor, a clamp over the cable to measure, or simply try to see if the way the setup is done, electrically speaking, I can derive. In thermal, in refineries, you can't really put anything inside to measure the pressure, which is the language there, is pressure, right? Everything. So what you do is to insert a temperature meter as a proxy, right? As a surrogate for the pressure. And to do that, you have to rely on different types of algorithms to figure out where to insert those sessions, those sensors. But anyways, I think your point, Kyle, is to make sure that this is done in a way that it doesn't become vulnerable, at least reduces the risk. And sorry to be again saying it depends, but it really depends on the setup that you have. We've been trying to constrain this as much as to internal computing capacity, trying to not rely on external models to answer our questions. So I know it's a very high level answer, but it's hard to be precise in this topic.
Absolutely, and these are 3 fantastic presentations. Janice, do we have any other questions coming in online?
There is a Q&A box at that you should be able to see. So there's one that thanks you, Dr. Wang, for your presentation. Nice to see and listen to you after a while. This is actually from Ali Malik. And his question is, can you please elaborate on function blocks in your system? Can I understand a function block as the ones created in PLC automation program? ?
Well, thank you, Ali, for raising the question. I haven't seen you for a while, and good to connect in this written form. So regarding your question, I think you're talking about the function block diagram used in PLC control. And the function block I'm talking about is a different standard. And the previous function block diagram is IEC 1131 used for PLC control, like a ladder diagram, instruction list, structured test. And that one is still time triggered, not event driven. The function block I'm talking about in my presentation is IEC 61499. And this standard is event driven. That's why there's 2 blocks. Putting them together on top is event input and output, make this event driven. Whenever there's an event arrive, it triggers internal algorithm based on finite state machine predefined and generate output. This can make it adaptive to the situation. Otherwise, if you use a conventional PLC control, everything needs to be predefined and you use a code and triggered by time. So that's the difference. But thank you for raising this question. I hope I explained and answered your question.
Okay, I don't see any others in the Q&A box currently. I do notice it is rather interesting, the intersection really of all three talks. And Vincent, your next to last slide, which listed future trends and opportunities, I certainly see augmented manufacturing workforce. Do you want to comment on that, as well as maybe some of the things that that Dr. Wang brought up?
Yeah, so when you look at, I mean, all the speakers are the same way. We are like researchers, and we are trying to like solve very, very complex problems. So we end up like collecting probably more data than we need. We are developing like very complex techniques and so on. But at the end of the day, when you look at who's on the receiving end of everything we do, that's going to be the small mom and pop shop somewhere in a small countryside, and they don't have any knowledge on anything we do. Sometimes they don't even have any kind of smart manufacturing implementation in their own facility. So all of a sudden, you are asking them to become expert in computer science and being able to run like artificial intelligence models, and they don't have any of that. Same thing with the new workforce, the new generation of operators of those systems. They know very well on how to run a particular machine, as long as they stay in front of the system at any given time. If they want to be able to run multiple systems at the same time, they need to have like a computer science companion in the form of an AI-based technique that support them in their day-to-day operation. And so that's where that's what I'm thinking in terms of like workforce development. We need to come up with a mechanism where it does not become we are not bringing fear on the manufacturing workflow by throwing like names like AI and FEM analysis and those type of things. It has to be like something very simple that those new individuals or those new workers will be able to appreciate and understand. They know that they have something that's going to support them. They don't necessarily have to understand everything about it, but they have to appreciate that it's here to help them and not like replace them.
You know, Vincent, you brought up a really good point that everyone is taking probably more data than they need right now. Every stage of the process, every piece of inspection. I'd be curious to turn it over to you and the other panelists. We talk about cradle to grave. So what does actually grave mean? What do you do with that data at the end? Where is too much? And how do you decide how to draw the line of keeping long-term data storage?
Yeah, perhaps I wanted to follow up on the previous question first regarding the workforce development, and before I go into the next question. For us, because I work at a university, we develop students, and the students may be the future workforce if they enter into the workforce, of course, but some of them may go to research institutes, study at university. And we had this debate recently, whether we should change our curriculum to provide opportunities for students to learn AI and related things, machine learning. Traditionally, mechanical engineering or manufacturing engineering focus on certain set subject topics that we wanted to train students. If we teach them to use ChatGPT or generative AI tools, how to use them, it can improve their productivity. They can generate a result which is excellent, but they may miss the process. So we are hesitating, because for student training, not only passing the knowledge to the next generation, but how to train them to become a problem solver, analyze, synthesize the situation, and generate a result. If we use AI tools and this analytical and synthetical task may be done by AI, the student don't understand why and how. In that case, this skill is lost. There's also debate that training for the AI models is ongoing and accelerating. At a certain point, the digital intelligence will be more than the human intelligence. Are we will be able to control the situation, or we lose it, becomes the slave of AI or the robots, machines, and so on, if their intelligence is much greater than us. I know some universities ban use of ChatGPT and generative tools. We are still debating. So this is related to workforce training. On one hand, we need to provide them with better tools for them to use. At the same time, we need to consider the long-term potential negative consequences that we may face down the road. So this perhaps also related to the Cradle issue. If we do not train students properly, we may send them to graves down the road.
If you don't mind, I would love to comment on this a bit. Change is happening, whether we want to embrace it or not. And how we prepare the next generation to solve problems, really, that means that we need to challenge them to think, not just to rotely go through their education in a checkbox sort of manner, right? I think that one of the things that you bring up is rather interesting, because I certainly think that we could make it fun and even make it, like truth or not truth, right? What came out of ChatGPT versus something else. There are ways to make this learning fun, but at the same time, how is it that we will be able to recognize when we have been outsmarted, when we're not smart, right? When it's been superseded? I think that's a rather disturbing scenario. Yeah.
If I may, I want to add to something. I mean, we should definitely look at how we educate our workforce. But I would also mention that in that workforce we have, and I think that's what Vincent alluded to, is the a number. I mean, the vast majority, especially in the mom and pop shops, they do not have training for cyber at all. They tend to trust on solutions that you see in over the counter, like saying an antivirus will solve my problems, and that's not the truth. So I think a key part of our success relies on how we build tools that do not require a big step learning curve for cyber decisions, and two, provide enough training for those tools. I mean, part of the Cymene work involves going and do audits in some of the partners, and what we've been seeing, there's a lot of lack of cyber hygiene. I mean, some basic things that should be done to prevent attacks, but also there's a reluctance in spending time and energy learning the tools, because you don't see the benefit. And that includes the cybersecurity side. I mean, if they don't understand, they tend to not even consider implementing, which at the end of the day is what is really holding us at this point.
So we have about 5 to 10 more minutes for Q&A. One of the questions that I've seen, and actually I put this in the chat to our hosts, but it would be great if you could address questions about how after the webinar they might find the recording, and how they for those that are interested in receiving a certificate of attendance, how that will happen, if you want to draw attention to that.
Okay, thank you all for your wonderful presentations. After this webinar, video will be posted on our webinar page. We will send the email to all participants, so also they will receive a certificate of attendance.
Wonderful, thank you.
I have actually a question for Dr. Wang. So I
Yes,
was
go
interested in his presentation, and my question is on your demonstration at the end, you had like one person controlling one robot. Can you control multiple robots using the same type of approach, or will this have to be the brain provides an objective, and on the robot side you have to distribute the workload between robotic arms or whatever you have? What's your take on this?
Yes, theoretically, it's possible for one-to-many application, because in the training command, there's a subject. The subject, you can specify robot A or robot B. If you want robot A to help you, you mention, think about robot A. But in reality, sometimes if you do not give very distinguished name, it's difficult to tell the difference between robot A or robot B. Perhaps I need to give a dramatic name. The brainwave is totally different. The idea in the future is not just to control a piece of hardware, a robot. It's to control your own hand. You control a robot like your third hand in a way, and it's well coordinated. Right now, we are used to control our both hands. But if we can send a command, neural command, directly to the third robot, we can treat it as the third hand of ourselves. And along the same line, we can have 4 and 5. So in that scenario, this robot is purely controlled based on our brain, but we have a long way to go. Theoretically, it's possible. The main challenge is signal processing.
Okay, thank you.
Well, I think without any other questions, maybe we just do a quick go round. Are there any closing thoughts? First, I'd like to greatly appreciate the participation of all of our presenters today. This is really, truly a unique opportunity to bring you together and to share with an international community. I thank our host, MDPI, also for providing the opportunity to us. And again, I know that Dr. Kurfus would have loved to have been here. I'm sure that he'll be eager to watch the recording. And again, we're both would be very interested in submissions to the special issue, which MDPI has placed the link to that in the chat. Any final closing thoughts from anyone?
Okay. Thank you all for joining us today. Now I will close the webinar, and I wish you a wonderful weekend ahead.
Yes.
Okay.
Okay.
Thank you, everyone.
Thank
Thank you very much.
Thank
Bye.
you.
Mhm.
Thank
Bye.
you.